conductor. Electromagnets are useful in part because their magnetic attraction can be turned on and off. In this video, a powerful electromagnet is used to move scrap metal in a junkyard.
Okay, so the good thing about them, we're going to learn about the theory behind the electromagnetism. So the basic concept is the scientists found that electricity and magnetism are somehow connected. When there's an electric current, there must be some sort of magnetism. And we use it to build machines, to invent different things. A good example would be the MRI. If you haven't used it before, I mean, you must seen it in the movies or in televisions. It's a medical equipment that the doctor used to take images of your brain, and it is basically a very powerful electromagnet. When it's turned on, the magnet is extremely powerful. Now let's watch a video about how powerful is a magnet in that MRI machine. So yep, this was when the machine is turned on, when the magnet is working. So you say it is quite powerful.
Yes.
Okay. Yep.
Whoa! So the force we're reading on that guy right now.
Okay, so in this experiment, those guys in the YouTube, what they do was they attach a piece of metal with a string, and they were pulling it, okay? And they were basically measuring how the force that the electromagnet exerts on the metal. That's the current reading.
That part of the magnet is close to 300, 280.
Yeah, pretty good.
Okay.
See what we can get.
Yep. So yeah, that's what happens. If they don't pull the metal in the middle back, the metal will fall on the wall, on the inside wall of the machine. So.
Okay.
No.
400 now.
And it's going to attach itself to the board.
Any second, it's going to start dropping, yeah. Just do enough.
There it goes.
There it goes. Oh, and that's all
And now, it is giving us a reading of 500 pounds. Whew.
Okay. In this time, they're going to put a metal on the chair. Remember, the chair doesn't have any metals on it. Okay. The only metals are those things they put on. Okay. And you can see that it is quite powerful, giving there's only a little piece of metals on the chair. Okay. So those guys try to pull the chair, but they can't. Okay, they can't stop. It's just too strong.
560. Ooh, ooh. We are at 700.
It's a menacing sound.
Yeah.
700 pounds.
Oh, it's about
oh. And we have jumped to 1300.
That's exactly really.
Yeah,
The
jump.
most magnetic stuff is right here, still on the top of the chair.
Whoa.
So we're just about to hit the sweet spot.
The
Keep going.
wheel is sitting.
Whoa!
Baby.
There we go.
Oh my god.
Okay.
What do we got now? No, look at it, 1700.
We are at 1700, which is far more than this thing.
You just relaxing it now?
Yeah.
Okay, so the there it
Oh.
goes. Oh,
No, it's up there.
1800. 1800.
1800.
It's
It
past
is past.
2000. Past 2000.
Oh,
No, we got it.
there you go.
This.
Okay. Okay. For electromagnetism. Okay. So let's learn the basic relationship, the behavior between current and magnetism. So assume if I have a current wire goes upwards like this. Okay. When there's a current, there will be it automatically produces a magnetic field. And how do we find that field? We're not going to use our right hand rule, but a different one. It's called the right hand grip rule. Okay, you'll find it in your notes. So what you're going to do is, if I have a look at this. If I have a current, if I have a wire that goes with the current goes up, okay, what I do is I use my right hand grip rule. I get out my right hand, okay, and remember the thumb is always in the direction of the current, okay, and I grip it. I try to grab it. Okay, I try to grab it like this. Okay, so my fingers tells me the direction of magnetic field. So in this case, if you're looking at the picture, I grab it. Yep, the magnetic field is going to circling around that the wire. Yes, and it is true if you're holding a piece of wire, and there is basically a magnetic field going around it in circle. And yep. So just let me label this one. Okay. Let's use blue color. So the magnetic field is going to be just circling around it. Okay. And this is, well, when the current is stopped, when the current has been cut off, the magnetic field is gone. Okay. When there's current, well, there must be a magnetic field. That's what scientists discovered. Okay. The reason why those wires doesn't attract any metal is because the current goes through them is really low. The really low current, and the magnetic field it generates is really low. Okay. Yep. So yep. But okay, let me show you it on paper. How does it draw? So in the exam, sometimes you have a question like this. Okay. Now, what they do is they show that. Okay. So you have a current coming out of the page, and the examiner asks you to indicate where is the magnetic field. Okay. So use your right hand rule. Okay. Right hand, grab it. Okay. Your thumb is always in the direction of current. In this case, out of page. They're coming out of the page. Just do it facing your screen. So then you have a rotation there. Okay. So what you do is you can label the magnetic field, okay, like this. Okay. Because this is basically the direction of magnetic field. Okay. The further it is to the current, the weaker it is. Okay. Okay. The most simple type of electromagnet is called a solenoid. Now it is all start with a theory. Okay, let me. Yep. So what they do is somehow, okay, we put a current in a circle. Okay. Say if I have a current traveling in a circle. Okay. Now, then when we do that, okay, try to picture this. Try to use your right hand grab rule to figure out the direction of magnetic field. Okay. So if I use my right hand grip rule on those wires, okay, now my thumb goes with the direction of the current, okay, and I grab it. Okay. So in this position, okay, the magnetic field goes inwards. If I travel along the circle, okay, if I twist my hand, okay, now in that circle, the magnetic field is always going inwards. Okay, and yep, no matter how do I twist my hand, it's going to be inwards. So imagine from outside, the magnetic field is going to come out from the outside of the ring. Okay? So in this case, we can label the direction of magnetic field like this. Okay? Go into the page, okay, inside the circle, and it comes out of page outside the circle. That's the magnetic field. Okay, now what people do next, okay, but how do we do that in reality? And what we did next is this. Okay, so what we did was, okay, we use a piece of metal. Okay, we use a piece of, let me use. Then what we do is we rotate wires around it. We wrap it with wires. We have wires wrapped around that thing. Okay, so then we connect this wire with a switch and a battery or a power source. Okay, this is done. So when we turn these things on, we will have a current, okay, flow in that direction. Okay, the current will flow. Yep, it travels like this. If we try to use our grab rule, okay, the right hand grab rule, we say that when the current goes in this way, okay, the magnetic field inside the circle, okay, look at your screen, inside the circle is going to be to the right, to the left. Okay. Just be careful, it's a mirror image with the webcam. Okay. The magnetic field is going to move from left to the right with all the circles if you do that twisting thing. And what we do is we can label the magnetic field. Okay. The magnetic field actually going to be like this, and it will leave the metal here. Yep, the magnetic field actually going to leave this thing behave like a magnet. Then we have our north pole here, we have a south pole here. Yep, you can do this thing. So this is basically a simple electromagnet. Okay, assume, yep, the current and down. Okay, Now let's do some examples. Do some example questions on this kind of thing.